Hello guys, nice
Hello.
to see you.
Hello.
Hi, how are you doing?
How about you?
Hello, Professor.
Hi, good afternoon. Hello. Okay, so last time we discussed how external magnetic field effects on conductors with electric current and derive some general equations which allow us to calculate this force exerted on a conductor with current, regardless of its shape and length. So we can integrate from 2 points which we choose. So also we introduced the concept of electric current loop, which is placed in some external magnetic field. And when we have such case, there is certain torque exerted on such current loop, and we calculated that torque. So I will start our discussion now from recalling the last equation, which we derived for the torque. And we will introduce one more parameter, which is necessary to and quite commonly used to describe torque created by some current loop. We will discuss some practical application on the example of amperemeter, which is instrument designed to measure the magnitude of electric current. And after that, we will switch to the topic focused on Hall effect. So let me switch to our slides. So we finished our discussion last time on Monday with this equation was torque as like in vector form, electric current multiply vector A cross product of vectors and vector B. So here we have vector product A and B, which stands for B magnetic field. A, this is vector perpendicular to the plane of the loop, and its magnitude is determined by the area of the current loop. So so now let us introduce one new parameter, which is the product of electric current and vector A. So that product is defined as the magnetic dipole moment. So we can write that this is equal to mu vector. And units for magnetic dipole moment, mu, are ampere times square meter. So if we have some coil which consists of n loops, let's say we have n loops, then magnetic dipole moment can be calculated coil as follows. We just need to multiply this number of loops by magnetic dipole moment of each loop separately. So that is current which flows through the loop times A vector. So now, taking this into account, we can write that the torque exerted on a current loop in external electric field, magnetic field, can be given by a vector product of magnetic dipole moment mu and magnetic field vector B. So that is what we need to know about magnetic, like torque exerted on magnetic, on current loop in magnetic field, which can be determined by this simple equation eventually if we operate with the parameter magnetic dipole moment. So we just need to know the magnetic dipole moment of given current loop, and by simple like vector product we can get the torque vector which is of our interest in this particular case. So obviously this fact that magnetic field exerts some torque or current loop has quite high practical value and can be applied in different devices. So in particular, such device as electrical motor, like actuator, that's the most common, one of the most common device where we transform electric energy into mechanical energy, and of course it includes formation of external magnetic field inside of which there is some current loop, means coils of the electric actuator, and they contribute to the creation of this torque, which starts to spin the shaft of the engine and actually convert electric energy into mechanical. So, however, this is not the only possible application. And also, I would like to show you one interesting system. Let me share my screen. So this is some schematic representation of electromagnetic ampermeter device, which is designed to measure electric current. So how does it work? We have some axis, like shaft, attached to the current coil. So here, this rectangular is our current coil. Also, this axis is fixed with some springs, which keep the orientation of this arrow in given initial position, which could be considered, let's say, at zero position when there is no current in the circuit. So external electrical circuit is connected to this current loop. So the resistance of this current loop should be very small. We don't want this resistance of ampermeter as a measuring instrument to influence the current in electric circuit. So we just want to measure it, but not to affect it. Since we connected in series, and parameters are connected in series, as opposite to voltmeters, the resistance of this current loop should be very small, much smaller than resistance of electric circuit itself. So in that case, when we connect it in series, the electric current, the same electric current, which flows through electric circuit, will flow through this current loop. And if we have current loop and external magnetic field, which here you see, we have permanent magnets placed just next to this current loop. So in this space where current loop is located will be some uniform magnetic field created by these permanent magnets. So if we have some current in this current loop, which we want to measure, obviously, if we have a current loop in external magnetic field, there will be some torque exerted on this current loop. So this torque via this shaft, like this axis, will be transferred and applied to the arrow. So it will compensate torque provided by these springs and will cause some deflection of this arrow. Obviously that the degree of this deflection, the angle of deflection, will be defined by the magnitude of electric current which flows through this current loop. So the larger current will flow in electric circuit, and thus inside this current loop of the ampere meter, proportionally, directly proportionally to this magnitude of electric current, will increase also torque exerted on this current loop from the side of this external magnetic field. So that means we will get different angle for position of this arrow for different values of electric current. So this is one of the most simple and straightforward design of ampere meter, a device which measures electric current. However, it can actually be very accurate and is widely used even nowadays in the world of these digital multimeters which measure everything. So this actually, this type of device can provide even higher accuracy than many modern digital equipment. So this is the like another example which is different from these trivial actuators, electrical actuators, different approach to find application of this torque exerted on current loop in external magnetic field. So also widely used in measuring electric current. So now I would like to switch to our new topic, which we're going to discuss. And that will be some sort of combination of electric current and magnetic field in certain way, which provides possibility to learn very important parameters about determine some unknown properties of metal or semiconductor materials. So going from the origin of this, it was found by Edwin Hall in 1879 that when we place some current carrying conductor in external magnetic field, which is perpendicular to the current direction, there will be some electric field created, which is perpendicular to both electric current direction and magnetic field direction. So this formation of this electric field, or in other words, it's called pole voltage at the edges of the sample in the direction perpendicular to the plane defined by electric current and magnetic field is called Hall effect, in the name of the scientist who first have shown this effect. So let me switch to a new slide. So we have more space, and let's consider the system we are interested in. So that will be the following. So we have some conductor. Let me define this axis also. Will be axis X, then will be axis Y, and axis Z. So we assume that there is some electric current flowing in the direction of axis X. This is electric current. The height of this conductor in the cross section will be D, and here will be thickness of this conductor T. So now let us consider two charges. Like in general case, we can have either positive charge or negative charge. In order to provide this current direction, positive charge should move along axis X. So this is direction of drift velocity vector, and negative charge should move in opposite direction because of different sign of the electric charge. So this is VD vector. So now we assume that magnetic field vector is oriented along axis Y. So you see that magnetic field is perpendicular to the direction of electric current. And when we turn on this, say, external magnetic field, there will be some potential difference between points let's say A, B, which are located at the edges of this conductor, and the line between these points A, B will be parallel to the direction of axis Z. So what is the reason for that? Actually, it is magnetic force acting on moving electric charge carriers inside this conductor. So if we now apply this rule of left hand, we will show that magnetic field, magnetic force F B is oriented towards like upwards along axis Z. Similar will be for negative charge, the same direction for magnetic force. It will be along axis Z. So both doesn't matter, positive or negative. Our charges will be deflected to the upper edge of this conductor. And in order to explain the origin of this potential difference between points A and B, between upper and lower edges of the conductor, first of all, let us consider some case with unipolar conductivity, so-called, means that we have only one mobile charge carrier, not both. So good example is either metal, where we have electron charge carriers only, or P or N type doped semiconductors, where we have majority charge carriers electrons which are negatively charged, or for P-type semiconductor we have majority charge carriers holes which possess some positive charge. So minority charge carriers can be neglected because their concentration is much lower. So in that case, we deal only with one type of charge carriers, either electrons or holes. So let us assume that we have some piece of metal and we have only electrons which are mobile and can move inside the bulk of this metal sample. When we have such combination of electric current and magnetic field, as shown on this figure, for electrons, they will be pushed by magnetic force towards the upper edge of the conductor. Means that because of this force, they will kind of accumulate a bit more closer to the upper edge of the semiconductor because there is this force pointing them to that direction. If we accumulate a bit more of these electrons at the upper edge of the conductor, they will create some space charge, negative space charge. Obviously, initially our piece of metal is electrically neutral. So if we create some excessive negative space charge next to upper edge of the conductor in the vicinity of this point B, that automatically means that in the lower edge of the conductor, we will have some uncompensated positive space charge created by positively charged ions of the like atoms of metal, which form the crystalline lattice of this metal. If we have at opposite edges of this conductor, at the top part of the conductor, excessive negative charge because of accumulation of mobile electrons, and in the bottom part, some excessive positive charge because of uncompensated positive charges of atoms of the crystalline lattice, since electrons are withdrawn from this area. There will be some electric field in between these regions. So here we have some excessive negative charge. Here we have some excessive positive charge. And obviously, we will create some internal electric field, which is like this electric field vector will be pointed from bottom edge of the conductor to the upper edge of the conductor. So this internal electric field is when we multiply it by the height of the conductor, d, will give us some potential difference, delta V whole, and that potential difference is equal to E electric field. We can call it E H, like whole electric field, times height of the conductor D. So that is whole voltage, which will be created between points A and B. So that is the physics, the origin of this, like physics behind the Hall effect and formation of this potential difference between points A and B, and formation of internal electric field EH, which is oriented perpendicularly to both electric current and external magnetic field. So after this explanation, we can provide some derivations in order to see how this Hall effect can be useful for us in order to determine some important properties of conductors or semiconductors. So as you remember from Hall effect, from Ohm's law in differential form, J, current density, is defined by the product of sigma, which is specific electrical conductivity, and electric field. In other terms, we can write that current density is equal to electric current Q times N concentration of charge carriers times mu times E. So this mu is called mobility of charge carriers. In other form, we could also write that this current density is Q times N times V D, and this is the drift velocity or drift speed. In this case, we don't use vectors. So drift speed, as you can see from these two equations, actually this stands for these two parameters. Drift speed is equal to mobility times electric field. So in other words, the definition of mobility will be drift speed of charge carriers at unit electric field. If instead of this electric field we put unity, then we will get the definition of mobility of charge carriers. So that is very important parameter because mobility defines how easily charge carriers can move in given material. And that is property of, like, one of important electrical properties of any material. What is important to highlight here, that we can measure current density, for instance, with this instrument amperemeter, which we discussed previously. So we can measure magnitude. We also can measure with voltmeter or just determine strength of electric field, which is applied to this conductor. So if we measure them, so from this equation, we can calculate sigma, which is electrical specific electric conductivity. Sigma will be equal to J divided by E. So we can measure both of these, J and E. Means we can get the value for sigma. That's already very good. It's important. Specific electrical conductivity is important parameter of materials. However, if we look here, we see that so these three guys here stand for sigma. We see that sigma is proportional to the product of charge concentration and mobility. So we don't consider Q because it's just a constant. So we know sigma, but with knowing sigma from this simple measurement of current density at certain electric field, we cannot distinguish between concentration of charge carriers and mobility because sigma is proportional to the product of these two parameters. So we kind of stuck because this simple current voltage characteristic measurement, which implies measurement of current density and electric field, does not provide us enough information to tell what is the concentration and what is the mobility of charge carriers in this material. Since these parameters are very important, it is necessary to develop some new technique which will allow us to determine these parameters. And this technique is measuring Hall effect. And let us try to go step by step in order to understand how it works and how it can help us, this measuring Hall voltage, how it can help us to determine these unknown parameters, concentration and mobility of charge carriers. So, as I said, in external magnetic field, there will be some magnetic force exerted on mobile charge in this conductor. Equilibrium condition will happen when magnetic force is compensated by electric force, which originates from this induced internal electric field, Hall field. So they will be oriented in different directions, and at some point there will be equilibrium. So we can write for magnetic field Q times VD times B should be equal under steady state condition to Q times EH. So that is equilibrium for condition for compensation of magnetic force by electric force. So potential difference between these points A and B, which is Hall voltage, delta VH, is equal, as we mentioned earlier, EH times T. And based from previous equation, we can write that it will be equal to VD times B times D. So now let us express VD, drift speed. So we know that electric current I is equal to Q times N, concentration of charge carriers, times VD times A, which is area of the cross section of the conductor. So from here, we get that VD is equal to I, electric current, divided by Q and A. So now keep in mind that in our case, the cross-section area A will be equal to D times T. So let us now express again this potential difference dVH, actually Hall voltage. That will be I times B times D divided by Q and A. So we just substituted instead of VD, its expression, this one. And also what we can do here, we can go from current to current density, because here we have I divided by A. So current divided by cross-section area, which will give us current density. So that will be J, current density, times B times D divided by Qn. So this equation let us write on the new slide. So we have more space. Potential difference, Hall voltage, will be equal JBD, JBD divided by Qn. And here we will actually put sign plus minus, because it will show the polarity, because it could be that we have positive, like negative potential at the point B and positive at point A, or in the contrary, it depends on the type of charge carriers. So actually the sign of this polarity, the polarity of Hall voltage will show us which type of charge carriers is dominating in this conductor. Because, for instance, if we consider electrons, we will have a negative charge accumulated next to point B and positive space charge accumulated next to point A. In the contrary, if we have positive charge mobile, that will be opposite. So positive charge next to point B and negative charge next to point A. So by checking the polarity of Hall voltage, already provides us information on the dominant charge carrier in this conductor, which is already very important information. So we know it's either electrons or holes. However, it's not only thing what we can learn. So then it is, we can rewrite this equation in a bit different form by introducing Hall coefficient. So we can also write plus minus J times B times D and times capital R H. So this is Hall coefficient. So if you look at first and second equation, you will see that Hall coefficient is equal to, so we can maybe even put it, write it without plus and minus. We can put plus minus here for Hall coefficient. It will be plus minus unity over Q divided by N. So plus minus, it's either positive or negative charge Q, and N is just concentration of charge carriers. So that means that if we know Hall coefficient, we can easily calculate concentration of charge carriers because we have this simple relationship. So it's just reversely proportional. How can we get the Hall coefficient? Let's us take a look at potential difference, Hall voltage, and this equation. From here, we can express RH as J, we have first delta VH divided by J times B times D. So now let us take a look on these parameters, which are in equation defining Hall coefficient. So potential difference between points A and B, we can measure. We can attach voltmeter and measure potential difference. We also can measure current density. We have some ampere meter connected in series to this conductor. We have information about magnetic field. We also can measure magnetic field. And obviously we can measure the height of this conductor. So here we have 4 parameters, which all of them can be experimentally directly measured. Means that we can experimentally determine Hall coefficient. If we experimentally determine Hall coefficient, that will be equal, so we can put here plus minus also, plus minus 1 over Qn. So we use all, like experimentally measure all these 4 parameters in order to get Hall coefficient. And from the relationship between Hall coefficient and concentration of charge carriers, we easily determine concentration of charge carriers. So that is the first step what has to be done in the analysis of Hall effect results in order to determine one known parameter, which is concentration of charge carriers. Now, if we know concentration of charge carriers, we can proceed further and determine also mobility, because we remember that sigma is proportional or actually we can write it's equal to Q times N times mu. So this guy we can measure experimentally. As you remember, I wrote that sigma is equal to J divided by E. So we can measure specific electrical conductivity. If we know sigma and know N, Q is elementary charge, then we can easily determine concentration of mobility of these charge carriers. So that is the beauty of this Hall effect, this technique, which allows us to distinguish between contributions of concentration of charge carriers and their mobility towards the total, like some synergetic parameter, which is specific electrical conductivity. So that's why this method is one of really not so many options to determine both concentration and mobility of charge carriers in. And it's really widely used in everyday life. So there are it's used in different devices, for instance, systems to measure strength of magnetic field. There are also Hall sensors, which are widely used in different devices and systems, which can control work of engines, for instance, and control the feed of electrical sparks in petrol engines and stuff like that. So some sensors for security based on Hall effects sensors, and also widely used this Hall effect in research in scientific world, because this is state-of-the-art technique which has no alternatives to analyze to carry out detailed analysis of electrical properties of different materials. So with this, I would like to finish our discussion today. If you have any questions.
May I ask?
Yes, sure.
Could you show previous slide?
Yes.
Could you explain why in the left corner QVB is equal to QE?
Because okay, 1 second. Let me go to another slide where we have some space. So let's consider in cross section from the side. We have, let's say, some charge carrier. It is moving, so we have VD, and here is magnetic field. So this will be FB, the magnetic force. So what will happen if this charge carrier, let's consider from here, moves to the left? Upon the effect of this magnetic force, it will be kind of deflected towards the upper edge of the conductor. And here we will have some kind of accumulation of this mobile negatively charged carriers. At the same time, if charges are kind of collected at one edge, at the opposite edge should be some uncompensated positive charges, because in total system is electrically neutral. And here we will have electric field, EH, induced electric field inside the conductor. So this induced electric field will exert some electric force, Fe, on the charge carrier. And when they balance each other, these charges will not deflect anymore anywhere. They will just move straight, because we will reach some steady state condition when magnetic force is equal by amplitude, the magnitude, to electric force. And since magnetic force is given as Q times VdV should be equal to Q times EH.
Oh, got it. Thank you.
Okay, you're welcome. So we introduced today this effect, Hall effect, and I tried to explain the importance of this technique and this phenomena. So it really finds wide application. So all of you who are going to work in field of solid state physics or semiconductor physics, you will definitely use this experimental technique to determine concentration and mobility of charge carriers in your samples. So kind of very fundamental and important for understanding why we need it, why we cannot just use simple current voltage measurement. So current voltage measurement provides only information about specific electrical conductivity, and that in its term is proportional to the product of concentration of charge carriers and their mobility. So if you want to know both, then you need to apply this Hall effect measurement in order to determine everything and get information about all these important parameters. Moreover, you can do these measurements at different temperatures under different environmental conditions and see how they impact on the on these parameters of given sample. Okay, guys, and thank you very much for attention, and see you next time on Friday. Have a good evening.
Thank you.
Thank you. Goodbye.
Thank you.
Thank you.
Bye bye.
Thank you. Goodbye.